So we've talked about central forces. Now let's be specific to gravity. So let's say we have two objects of mass capital M and of mass little m. We know that the gravitational force has a magnitude which is g times the two masses divided by the distance squared, where the distance is r, and then we have an r hat, where there's a minus sign, and we need to be careful with this mathematical object, but we know that the force on this one will be that way, and the force on this one will be that way, and they both will be captured by this expression. But let's say we have a more subtle situation where instead of point masses, right, more realistic situation, we have something like a distribution of mass over some region of space. There's some volume here. So we replace this kind of thing, and here we still have our object, our point object of mass little m. We now have to replace this expression with something that looks like this. Right, so we have f, let's maybe, so we recognize that we're going to be integrating, because we can think of little pieces of this massive object, and every little piece feels a force, and the force between that little piece, say the little piece here, and this will be along this line, so it will be that way here, and here it will be that way, and so on. We have to integrate all of that. So we actually need a coordinate system. So let's say we have something like this, and the origin of our coordinate system. We go to these little, let's say little boxes, infinitesimally small boxes, infinitesimally small volume elements. And so we have, vectors that in some coordinates, say r prime, points to that little box, and that little box is a distance from this massive object. That's what goes into here, and this is an r vector, and maybe we could use a different color here, but let me try to get a different color. Realize that there is a vector, say capital R, pointing in this coordinate system to where that object is. And so our f gets replaced. We have a minus g times little m, but now we end up replacing this object with an integral over some volume that depends on the density. The density could change from place to place. So we integrate over a volume, this volume, and we have some density that needs to be specified, and we want it in the coordinates given here, right, r prime, so we can integrate over that. And we divide by this r. Every little piece of this object has some distance r, which is changing. Right, so this r here is changing, and we integrate. Well, we need the r hat, so we have an r hat here. We need to write that down in the specific coordinates, and we integrate over the volume dv. And so we also want to note that well, I just wrote this as a magnitude, but this is really a vector r, and that vector r is related to these two. So we also have that little r is big R minus what we called r prime. And so this object is effectively well, we square it, of course, so it's a scalar object that involves the magnitude of these other vectors, r squared plus r prime squared minus 2r prime cosine of an angle associated with these vectors. And so we'll look more into this kind of expression because we are now dealing with extended massive objects where the density can be different at different locations.